So as our first step in the example, let's just review the study graph that we've been given. So we have this views to direction, and that's been provided by the refinery team. And again, what we're really after doing is thinking about where the kind of the X location and the Y location of those 6 different tower blocks could be, so that we can then maximize the total views in direction 1 to the south and direction 2 to the east. Okay, so what's the optimal arrangement so that we can kind of achieve that? So if we start looking at really what's available for variables, we have the X and Y location of building 1, building 2, building 3, 4, 5, and 6. Okay, and they all have kind of high and low values. Sort of, I guess, specific areas they can be kind of within their blocks, because they can't kind of shift infinitely, but you can kind of control how much latitude you want to give to have them move around. Okay. And then there is a lot of logic in here, which is really all about creating the different buildings. So create the building 1 box. It has a length, it has a width. You could change all these. These are really what I'd call constants at this point. Okay, you could make them more variables if we were kind of thinking about, creating a total volume of space and trying to kind of create that space by changing the length and the width in addition to the location, but that'd be a little more complicated. But for each of these, we're just basically going to create a cuboid, okay, which is basically a 3D cube, or a cube, okay, by the corner locations, and then translate it around in the X and Y direction. So that's all that's going on here, is we're creating 6 of those different blocks. The next chunk of the logic is really all about going through and trying to figure out the different faces, okay, towards the north, the middle, and the back group. Okay, so this group, and that group. Okay. Then we're basically going through and just calculating rays that do not hit the front row. Then we're calculating the rays that hit the middle row, and finally the rays that hit the back row. So what this is all doing is, from some sort of data points out here, it's just projecting rays back and seeing, does it actually hit those faces? Okay, we have the faces on kind of the south side and the east side. We're trying to figure out if those rays can actually hit those faces. So it's all a lot of ray analysis. So once we've gone through and kind of created those different surfaces, we can do some just different ray projections. And there's this intersection create isovist, okay, which is a function which is all about kind of creating rays within specific angles, and then ultimately trying to figure out really once we have those rays, we're trying to figure out whether or not they're intersecting or not. Now, the logic behind this gets pretty complex, so I don't expect that you'll kind of be able to dive right into the logic and kind of immediately kind of unpack it. But again, if you're doing some sort of a view analysis, go ahead and take a look at this, because there's some good examples in here from you to learn from in terms of the types of nodes that are useful for this and really how you can tie those nodes together. The net of it all, though, is we're ultimately going to go through and just report the total number of rays that hit the middle or back row there. We're going to hit the total number of rays that hits the middle or back row. We don't actually have to consider the rays that hit the front row, because those are kind of going to be constant, or they should be constant. Just given the spacing here, but again, we could add those in there too, but we're just going to focus on the ones that are potentially blocked. And we have these 2 different metrics then, view 1 and view 2, and that's really ultimately where we're going to try to be optimizing. Okay, let's go ahead and think about how we can use this then in our refinery study.